But the important point here is don't rely on just calculating things. Think about what the system is doing and see if you can predict in advance what's going to happen. And then the calculations really should just be a check on your thinking. When physicists do research, it's very rare that they go and do an experiment or a calculation without any idea what's going to happen. And when they do an experiment or a calculation without any idea, usually they don't get what they expect. They don't get the right answer. They make mistakes. So let's think about a certain situation. We'll do the famous rocket problem. Okay? You have a rocket, and we're going to be out in the middle of space somewhere. There's my rocket moving this way. And somehow this rocket accelerates in the middle of nowhere. How can it do that? There are no external forces. In fact, I think in the late 1800s, people thought this was impossible. It was impossible to accelerate a rocket out in space. Their logic was there's nothing to push on. All right? So when I push on something, right, I can make that, I can go backwards, right? Like if I shoot a rifle, there's an action-reaction that shoots me back. Actually, if they used the rifle analogy, they might have gotten to understand what's going on. So the answer is to just use conservation of momentum. The thing they didn't have in their head, the thing they missed, was that the mass of the rocket doesn't have to stay constant. In other words, you throw mass out of one end, and the rocket will go the other way. Right? That's how it works. All right, so let's do that. We'll imagine there's a rocket moving with velocity v in that direction. So speed v in that direction. It's not a constant. All right, this thing's going to accelerate. How is it going to accelerate? It's going to shoot out gas. So we have gas shot out this way. All right, and we're going to shoot it out with a velocity. It's going out this way relative to the rocket of v, some ejection velocity. Okay, so that's relative to the rocket. But relative to some inertial frame, what would it be? It would be v minus ve. Everybody see that? So the rocket's going this way with velocity v. Relative to the rocket, we're shooting out gas at a velocity, a speed v sub e. Right? The e stands for ejected. Right? The ejected gas. All right? So now we have that. And the amount of mass coming out, we can call some delta m. And then the rocket has a mass, let's say, m sub r. But that's not constant. That changes. Okay? So let's use conservation of momentum. All right? So let's see. We can imagine that at every time, we start out with a, so at t equals 0, or at t equals sometime, let's say 0, all right, it's moving with straight velocity v. So we have m. Actually, I'm going to just not use rocket there. I have m times v. So the m stands for the mass of the rocket plus the fuel that is in the rocket. Okay, so that's the initial momentum. All right, so we're going to use conservation of momentum. So this is the initial momentum. All right, so then that's got to equal the final momentum. All right, so what is the momentum of the different parts? The momentum of the gas is just delta m times this. So we can write that in. Delta m times v minus VE. All right? So that's the gas. And now we have to ask, what is the momentum of the rocket, finally? Well, it's its mass. But what is the mass? It's no longer m. It's m minus delta m. Right? That's the mass of the rocket now. Because it lost a certain amount of fuel, delta m. And we don't know what its new velocity is, but we know it gained velocity. So it's v plus delta v. All right, so that's our situation. Okay? Now we'll just do a little bit of algebra, and then we'll have to do a little bit of calculus. Okay? So I'm going to just multiply everything out. So this gives me mv. Now remember, you should be doing this in your head before I do it. You should know what I'm going to write down. All right? It's not that specially doing algebra. You guys can do algebra as well as I can. Some of you can even do it better. So there's that. V sub E plus mv plus n delta v minus delta m v minus delta m delta v. All right. So we look at that and we see, does anything cancel? And the answer is yes. This cancels with this. So that goes. Anyone see anything else cancel? What? This thing, right? Cancels with this thing. OK. All right, so we're almost there. Now, we're going to take limits as delta m goes to 0, because we want to do this continuously. The gas is coming out continuously. So in the limit that delta m goes to 0, we know that delta v will also be very small. This term only has one delta in it, so it has one small factor. This term also only has one small factor. But this term has two small factors. So this term is negligible. Negligible. Because it has two tiny, tiny factors. All right, so we can ignore it. So we're left with a pretty simple result. 0 equals minus delta m v sub e plus m delta v. All right? And when I make that a derivative, I get dv dm. What does that equal? VE over m. All right? So this dm is m is the variable, and that's the derivative. I really probably should make this a capital. Okay? So the question is, what kind of function, when you take the derivative, gives you 1 over? Or you could do the integral. Some of you know how to do integrals, some of you don't. But what function, when you take the derivative, gives you 1 over the variable? So you take the derivative of a variable, you get 1 over. What function acts like that? Anyone remember? Remember before we had the exponential function. That's where you get the same thing back. But there's a function that if you take the derivative, you get 1 over the function. Anyone remember what that is?
No.
Yeah, the logarithm. So you take the logarithm, you get 1 over. So the derivative of log x dx is 1 over x. So that's just like what we have here. So this implies that v equals ve log m plus some constant. Right? You always have to add in a constant. Because if I take the derivative of v, I will get that back. All right, so there are different ways of writing this. Notice that this constant is not v, the initial velocity. If I put in v equals initial velocity here, then that would say that m would have to be 1. So I'd like to do that. That means I have to add in 2 constants to make that work. So rather than going through a lot of detail, I'm going to write v equals the initial velocity plus ve log of the mass over the initial mass. And that'll work. Let's see why that works. When we're at the initial situation, v equals v initial, the mass will equal the initial mass. What is the log of 1? 0. All right, so that's why that works. Okay? Now, in order to make this more transparent for those of you who know calculus, I'll do the same thing with calculus. So I'm going to do an integral. So I integrate from v initial to v and from m initial to m. And so I get right away v minus v initial equals ve, the log of m from m initial to m. And that equals ve log m minus log m initial. And that equals ve log m over m initial. Okay? So if you know how to do integrals, that's the way to do it. Okay? And remember the property of logarithms. The log of a minus the log of b is the log of a over b. Right? Just like the log of a times b is the log of a plus log of b. All right? So we have this. Supposing we have a rocket, it's starting from rest out in the middle of space, and we need to reach a certain speed. So v initial is what? We're starting at rest. V initial is what? 0. All right. So we have that ejected velocity ve, and the mass of the rocket without any fuel, I'm going to call m sub r. And the question is, what's the minimum amount of fuel needed to do this? So we're going to use this result here. We know v initial is 0. All right, so I'm going to write v equals ve. And then I'm going to write the mass plus the mass of the fuel final all over the mass of the rocket plus the mass of the fuel initial. Okay? Everybody good with that? So in order to have the minimum case, what's the minimum amount of fuel I need to add in? What can I say? What would be the minimum case fuel needed? Is there anything I could say about this or this? 1. What would be 1? If I put 1 for what? What do I want to put 1 for? If I put 1 in here, I get 0, so I haven't reached my velocity. So I'm reaching a particular velocity v, that's given. The ejection velocity v sub b is given. The mass of the rocket is given. And I need to know the minimum amount of fuel needed to get this rocket up to that speed v. All right? So somewhere, so this is the fuel that I have. Right? This is the fuel that I'm solving for. I'm solving for this. The fuel that's in the rocket initially. What will be the minimum case? Say that again. That's right. This would have to be 0. Very good. Everybody see that? Because if I have fuel left over after I've reached V, then I could have done with less fuel. Right? So I'm there. Okay? So I have that 0. So I can write this as VE MR over MR plus, I'm just going to write the fuel, initial. Right? And I can do a little simplification. So I can write this as 1 over 1 plus M fuel initial over MR. Now, if I then solve for MR, whoops, I forgot something. Anyone see what I forgot? The logarithm in here, right? All right, now how do I solve for this thing? What do I do to the equation? If you have a log in an equation, how do you get rid of the log? How do you do that? If I have y equals log x, how do I solve for x? How do you do that? You just stare at it forever? What do? Say, what? E to that. All right? So I have that. I'm going to take that over, so I get e to the v over ve equals 1 over 1 plus mass of the fuel all over MR. All right, then I can cross multiply, solve for things. I think I'm not going to do that. All right, you could do it. All right? Now, another thing you should ask yourself is, if I divide the rocket in half, so I send 2 rockets going, do I need more, less, or the same fuel? I'm not going to answer that, but you should. All right, solve for the rocket fuel and see if that tells you whether you need more or less fuel if you divide the rocket in half. So you do 2 rockets. All right, so m sub r is half as much for each rocket. And you want to find out if you need more fuel or same or less. Okay? So this is the rocket problem, right? How it works. So it's a good application of the conservation of momentum. Okay? All right. I made an error in the very beginning. I would have noticed the error if I put some numbers in or looked at it more carefully. So this part is correct at this point. But this is the mass of the fuel. And we want to write down things in terms of the change in the mass of the rocket. The change in the mass of the rocket is minus the mass of the fuel, because the rocket's mass decreases. So I have to replace delta m with minus capital delta M. So I get a minus sign here, which I didn't have. All right? And then when I do all this, I get, instead of what I had before, I get that the velocity equals the initial velocity plus v sub e times log of the initial mass of the rocket divided by the final mass of the rocket. So I could write that as final. Okay? The initial mass will be bigger than the final mass. So this will give a positive over here so that the velocity actually increases. Otherwise, I get a negative. It doesn't even increase. I get a negative number. All right? So in my little example problem, I redid it over here. And you can change this up here. It should be m initial on top rather than m. OK? As I told you early on, you have to watch me. This is the expression we use in English. You have to watch me like a hawk. You know what a hawk is? It's like an eagle. It's a certain kind of bird that is very good eyesight. So you have to watch very carefully, because I will make errors. And I did make this error here, even though I had it correct in my notes. All right. All right, I'm going to do a little experiment here. I have two objects here. They're pretty different. I'm going to drop them. Did they reach the ground at the same time? Did they? Yes or no? Yes. That's odd. OK. So these two objects, they have different masses, but more importantly, they're really different shapes. And throughout this course so far, I have treated this object as if it was a little point in space. Why can I do that? All right, so we're going to answer that question right now. Why can I do that? Why can I treat this object and this object as if they're points, point masses, as if the object is very tiny? All right, why can I do that? All right, let's work that out. So in order to figure that out, I'm going to imagine every particle inside this meter stick. It's made up of atoms, right? And I'm going to look at the forces on every single particle in this object. Some of the forces are due to other parts of the object, other atoms in the object. Those are called internal forces. And some are due to things outside the meter stick. What do you think those are called? What are they called? External forces. Internal, external. All right, so let's write Newton's second law. All right, so Newton's second law for each particle. So I have a mass inside times its acceleration. Maybe I'll just write it out as its acceleration. OK? And I can even put a little vector on it. So it's due to all the internal forces, J not equal to I. All right? So these are the internal forces. but I have to add in the external force plus the external force on I. All right, so you notice, I guess I can write this as IJ. So this is the force on I due to J. Force on I due to J. All right? You can't have a force on yourself. That's why J does not equal I. Any questions about this formula? All right, now I'm going to do the following. I'm going to sum up over all the particles. So I'm going to put a big sum over I here, and a big sum over I there, and a big sum over I there. Okay, so I sum up all the equations. For this ruler, there's like 10 to the 22 equations to sum up. A lot of them, because there are a lot of particles in here, a lot of atoms. Okay. Well, there's not much I could do about this, but there is something I could do about this. Any ideas? So I have a force on I due to J. But when I sum up all the particles, I'm going to include like if I have a particle number 2, I'll have a force on it, 1, 2. But then when I sum up over I then have a force 2, 1. So they will all cancel out. By which law? Newton's third law. So this equals 0 by Newton's third law. And this thing is just the total external force, whatever that is. All right. So now I have a nice formula that this equals this. Now we make a definition. This is a definition. And when we make a definition, we use that. Usually I would put it on the other side, but I'm going to do it this way. I'm going to say that's the total mass times the acceleration of the center of mass. All right? When I do that, that defines what the center of mass acceleration is. So I can say the center of mass acceleration equals the sum mi a sub I all over the total mass. If you want, I could write total mass. Okay? All right. Well, I can then define a center mass velocity and a center mass position just by the following. All right? Notice all those work, because when I take the derivative of this to get this, everything's a constant in here except r sub I. And so the derivative of this is v sub I. And then when I take another derivative, I get a sub I. Okay? So this is called the center of mass. And you calculate it by doing this. For symmetric objects, like this guy, is reasonably symmetric about the middle, the center of mass is at the geometric center. So it's right here in the middle. I have 50 centimeters. All right, same thing for this piece of chalk. Okay, for a ball, it's at the center of the ball. That's where the center of mass is. For somebody like you, if you stood up, where do you think your center of mass is? Who knows? Depends on how your body is shaped, where it's going to be. All right? But one of the things we do when we're worried about falling down is we stoop, right? We walk carefully like this if we're on ice or something like that. Why do we do that? To get the center of mass lower to the ground, and we're less likely to fall over. And we'll learn a little more about that when we talk about torque and angular momentum later on. Okay, so this is the reason why we can treat an object like this, an extended object, like a point. What we're doing is we're treating this motion as the motion of the center of mass. Here's the total mass. And it's just given by the total external force. So that's what we've been doing. All right, so now I want to apply some of these ideas to what you will be looking at in your discussion sections. So the first result I'm going to show you is that if you take a ball and you hit it, and it hits another ball that's at rest, the two balls will go off at an angle. That angle is always 90 degrees. Why? All right, so we're going to figure that out. So this calculation is pretty easy to do. So here's the situation. We have an initial ball, usually called the cue ball. So this is the cue ball. It's going off like that. It hits another ball. This is called the object ball. And the two will go off at an angle. This could be the object. And this could be the cue ball. And this angle would be a right angle. I want to prove that. All right, so we'll call this velocity the object velocity, and this velocity we'll call the cue velocity. All right, and we'll call the initial velocity that. Okay, everybody with me? So the cue ball and the object ball, they have about the same mass. So we don't have to worry about mass. We could just say it's 1 for us. So momentum. All right, so I'm going to write down the momentum. And I'm going to divide by n. It's just VI, and that's going to equal VO plus VC. All right? So there's no, the mass is the same for all the balls, so it cancels out in the equation. Everybody with me? These collisions are very close to elastic collisions. So they're very close to elastic collisions. So that means VI squared is equal to VO squared plus VC squared. All right? It's an elastic collision. Now I'm going to do something tricky. I'm going to take the dot product of this equation with itself. So I get VI dot VI. And that's equal to V0 plus VC dotted with itself. All right, so let's see what that is. What's the dot product of a vector with itself? If I have a dot product, remember the dot product is A, B, cosine of the angle. So what would the dot product of a vector with itself be? It's just the square of the magnitude. So that gives us VI squared equals. And then when I multiply these out, I get VO dot VO, VC dot VC, and 2 of VC's dot VO. So I'm going to get VI squared plus 2 VO dot VC plus VO squared. All right. Make sure I got this right. All right. So I have this equation and this equation. What do you think I should do? I have 2 equations. Can I do anything with that? Well, you subtract one equation from the other. So I'm going to take this minus that. So I have minus VI squared minus VI squared, VO squared. Oops, I made a mistake here. You're not watching. Okay. No, VC, right? VC. Yeah. And what do I got here? Minus VC squared. All right, so I subtract. This gives me 0 equals that cancels, and I have 2V0 dot VC. So I've finished the proof. Why? If the dot product is 0, what can you say about the 2 vectors? They're perpendicular. Okay. Now, in an actual pool, these balls have kinetic energy. And so it's a little tricky. They have rotational kinetic energy in addition to the translational kinetic energy. So this is still true. This needs to be modified a little bit. But to a very good approximation, this still holds true. All right? And pool players use this all the time. And they try to estimate when they hit the ball, they not only worry, you know, in pool, the cue ball better not go in a pocket. That's bad. All right? So when you try and get the object ball in a pocket, you avoid the cue ball going in a pocket. So if you have a situation like this, there's the pocket, and there's a pocket, and you're hitting it like this, if that's a right angle, you're likely to run into a problem. All right, so you have to deal with that. And what you do is you put spin on the ball is one way that you can deal with it. You make the kinetic energy of rotation bigger. All right. So I don't have time right now to go into that part. But let me tell you a few other interesting things that can happen. All right. When a ball rolls, or a cylinder rolls, usually it can roll without slipping, but frequently it rolls with slipping. What does that mean? All right. Without slipping means the following. So a ball rolling without slipping. And this is what you have to pay attention to when you're playing pool, because balls usually are turning. So if this ball is going like this, and let's say I put a dot there. Here's the center mass. When this ball rolls like this, and it moves across the table, and it comes back so that this goes around and comes back to where it is, this distance here, that's r, that distance is 2 pi r, right from there to there, if there is no slipping. Okay? So the velocity of the center of mass equals the velocity of this point on the surface. We can say surface. That point on the surface. If it's not equal to that, then it's slipping. Okay? Now, you might say, how do I make the ball roll without slipping? Okay? Your first thought might be, I should hit the cue ball right at the center. Maybe that'll do it. The answer is that will not do it. The ball will initially start slipping as well as rolling. Turns out, and we will prove this later, that in order to hit it so that there's no slipping, you have to hit it at a height 7/5 r. So if you hit it right there, you will get the ball rolling without slipping. So it'll just roll without slipping. What happens if you hit it somewhere else? What happens to the ball? Okay. Well, if you hit it up here, it's going to roll more than it needs to roll. Right? It's going to be spinning faster than it should to just have rolling without slipping. So what does that mean? So that means this thing is rolling faster. So this will actually be slipping a little bit this way because it's rolling faster than it should. And so there'll be friction force that way on the ball. And the advantage of that friction force this way is it's going to slow down the extra rolling. And by slowing it down, it'll slow it down until the ball starts rolling without friction. Okay? I don't think I have time to go through the other cases, but if you hit it here, it'll do a similar thing. Here, you get backspin. And that'll cause the particle, the spinning. At first, the friction will cause it to slow down that backspin so that it comes to a point where there's no spin at all. And then the friction will cause it to have forward spin, top spin again. And it'll keep having that top spin until it gets to the point where it rolls without friction. So whenever you hit a cue ball in pool, eventually, assuming you don't hit the end of the table, eventually the ball will roll without slipping. All right. Now, remember we derived the case of hitting a cue ball, hitting an object in one dimension, where the initial object was sitting there, and then you hit it in an elastic collision. Do you remember what happened? We derived that last time. What happens? What happens if I take a ball, I have a ball here sitting at rest, and another ball coming in, like that, hits this. They both have the same mass. What happens? So the cue ball will come to a stop, and the other ball will go forward. If you try that, and you will get a chance to try that, it will not work. The cue ball will keep rolling either forward, or it might even come backwards a little bit. It will not come to a dead stop. But a good pool player knows how to make it come to a stop. So what you do is you hit the ball a little below the center, giving it backspin so that eventually friction will make the ball have no rolling. But the trick is you have to have it hit it so that it doesn't roll exactly when it hits the object ball. That's the trick. So that means the further the object ball is away from the cue ball, the lower on the cue ball you have to hit it. If it's close by, you hit it close to the center. If it's further away, you hit it lower and lower. So you'll get a chance to try that out and see if you can make the object ball stop when it's hit by the cue ball, all right, using this idea.